Okay, terminology and examples. First of all, suppose a set S has n distinct members, then we say S is a finite set, and we write it like this. We use this absolute value notation to talk about the number of elements in this set. So n is going to be equal to the absolute value notation of S, and we call that the cardinality. So the cardinality is just a way to say how many elements a set has. Then we have something called the power set of S. And the notation we use is this little script P. So script P of S is the power set of S. And it's a new set that consists of all the subsets of S. So let me show you an example. Let's take S to just be the set that contains A, B, and C. Then the cardinality of S is just going to be it's going to be the number of elements inside the set. It has 3 elements, so the cardinality of S is just equal to 3. Now, what would the power set of S look like? Well, it's the set of all subsets. So the subsets are going to consist firstly of the empty set. Don't forget that one. That's a subset of every set. It's also going to contain all of these sets that just contain single elements. They're called singletons. So I have the set containing A, the set containing B, the set containing C. It's also going to contain AB, because AB is certainly a subset of S, because every element in AB is inside of S. Likewise, it'll contain the set AC, the set BC, and the set ABC. That is all of S itself. So this entire set of all of these 1, 2, 3, 4, 5, 6, 7, 8 sets is the power set, because each one of these 8 sets is a subset of my original set S. So that leads us to the interesting conclusion that the cardinality of the power set of S is equal to 8. And it turns out that, actually, let me go ahead and shrink all of this stuff up here so I can have some more room. It turns out that if a finite set S has cardinality n, then the cardinality of the power set of S is equal to 2 to the n. So the cardinality of the power set will always be 2 to the power of the cardinality of the set. And when we get to the section, the chapter on mathematical induction, we'll get an idea of why that has to always be true. All right, what can we do with sets, set operations? So the first one is we can take the union of 2 different sets. So in Venn diagram terms, so I have my universe, I have a set A and a set B, and the union is what you get when you stick both of those sets together. So it says that this little U stands for union, that A union B is the shaded area. So everything in A is shaded, and everything in B is also shaded. So the union of A and B, in set builder notation, A union B is equal to all X such that X is in A or X is in B. Now remember, this is the mathematical OR, because that allows for the possibility that it's in both. And this is also why I told you that when you were drawing OR, this notation for OR, be careful that you had that point on it, because when it's curvy like this, that U, that's a different notation. This is a notation we use for sets. This is a notation we use for propositions. So the union is what you get when you stick 2 sets together. So quick and easy example. Let's let A, be, we'll say the set 1, 2, I don't know, W, and we'll let B be the set 0, pi, Z. So then to write the union, A union B, go back to the definition, always go back to the definition. The union of two sets is going to be every element that is inside of A or it's inside of B. So I just list all those things out. So A union B is going to consist of 1, 2, W, 0, pi, and Z. So that is the union of those two sets. After union, we have what is called the intersection. So as a Venn diagram, I have my rectangle that I'm not going to forget, my universal set. Then I have a set A and a set B. And then this upside down hump is called intersection. So A intersection B, where A intersect B, is what's shaded in, and it is what they share. It's the overlap. Okay, that's how I want you to think of intersection. It is the overlap. And in set builder notation, A intersect B is every x such that x is in A and x is in B. Again, that same thing I told you about. Make sure you use the sharp point for and, because the curvy one is for intersection. The curvy one is a set theory notation, and the sharp pointy one is a logical proposition notation. So just like before, let me show you a quick example. Let's let A, I hate that color for this. Let's go back to blue. So I have A, let's make that the set 1, 2, 10, 12. And we'll let B be the set 0, 2, 10, 20. So that means A intersect B is going to be everything that they have in common. Now, the only elements that are in both A and B, 1 is in A, it's not in B, so it's not in the intersection. 2 is in A, 2 is also in B. That means that 2 is in the intersection. 10 is in A, 10 is in B, so 10 is in the intersection. 12 is in A, 12 is not in B, so it's not in the intersection. Now let's look over at B. 0 is in B, 0 is not in A, so it's not in the intersection. We've already done 2, we've already done 10. 20 is in B, 20 is not in A, so it's not in the intersection. And so that's everybody. This is the entire intersection. It's just the elements 2 and 10. All right, so we are in the home stretch now, almost done. Next, I want to define what's called the complement of a set. And the complement is just what's left over when you remove a certain set from your universal set. So here's the Venn diagram. My universal set, U, have my rectangle. Never forget that when you're drawing a Venn diagram. And then I have this set A inside my universe. And I have this thing called the complement of A. So the notation is A with a little line over it. So here in the Venn diagram, it says that A complement is shaded. So basically, I've shaded in everything except for A. So the complement, again, is what you have left over when you remove the set. In set builder notation, the complement is going to be every x in the universe as long as x is not inside of A. That's the complement. So here's an example. Let me take my universal set to be, let's be a little bit more sophisticated this time. Let's take the universal set to be the natural numbers. Okay, so that is the set that includes 0, 1, 2, and so on. And then I'll take A to be the set 0, the set that just has the single element 0. So if I do my universe, so then A complement is going to be everything in my universe except for 0. So I'm going to take my universal set up here, and I'm just going to remove 0 from it. That's going to give me 1, 2, 3, and all the other numbers. And notice that this is exactly equal to what we before called the positive integers.